Okay, yes, we started recording. Excellent, excellent, excellent. Okay, hello. Welcome all to the second SPAR round for this year. This SPAR round was a sprint, but it was a bit of a long sprint. It had 8 problems, eight sort of more simple ones to test your applications of the more basic data structures and algorithms. I hope you enjoyed the contest. This is the editorial. We're going to be running through the solutions. Congratulations to everyone who participated. Particularly the team, I think Team Singular, who full solved the table flipping team from UNSW. But yeah, no, hope you enjoyed. Let's get started. So we're going to go through the problems from what I think is the easiest to the hardest, starting with H, which is hit the road, reference to hit the road jack. We have a list of integers, and we want to remove an integer such that the largest gap in the list is minimized. So what we can basically do is pre-process the list to figure out what the existing gap is. Then we can iterate through the list, comparing elements that are 2 apart to see what the new gap would be if we remove that particular element. So I have a diagram here. So you go like 1 and 3, 2 and 4, 3 and 5, blah, blah, blah. And then take the minimum gap. If you can remove an element without making the existing minimum gap bigger, that's already amazing. Otherwise, you can just take the minimum one that you would have created. Fitting bits, similarly easy. You want to take some power of 2 block of bits to store an integer up to some given number. Now, the constraints in this problem are very small. There are only 7 possible power of 2 answers, 2, 4, 8, 64, and you can just try them all in order. You can do some math stuff to try and figure out what the best one is a little bit faster, but since there's like such limited answers, like why would you risk it? I think it's better to just use the simple approach here. The next problem is D, which is Duke's decree. This basically involves sorting a string with a bunch of relations between some of the letters. So if A is less than B, then all of the A's have to come before all the B's, etc., etc. Now, importantly, if A is less than B and B is less than C, that implies that A is less than C. So, we have this like transitive relationship. We can use Floyd Warshall on the relation graph, where there is a Boolean that is true if A is greater than B. Or you could also do A is less than B. You just have to pick a convention. So yeah, Floyd Warshall, A of B is an A greater than B. And then you can do, 26 iterations to find all of the letters that should be greater than the other letters. If while you're doing this Floyd-Warshall relationship, you find that the Floyd-Warshall of A and B and also B and A are true, that means that A has to be either less than or greater than B, and then B has to be less than or greater than A, whatever convention you choose. So there must be a cycle. So the answer is impossible. If you can get an answer, there's a couple of ways to actually figure out what that is. One of the things you can do is use a topological sorting algorithm to figure out what the ordering of the letters should be. You can also write a custom comparator that actually uses the result of your Floyd-Warshall relationship to figure out which letters should be bigger than the others. Both approaches work. The next one is problem C, a bit of an annoying one in terms of input-output, but quite a fun one. I enjoyed it a lot. So we have to write some color C1 as like a big string that will encode what the word is. And then within that string, we need to put a littler string as part of the values that are not empty to sort of hide that within there. Now, because the question is quite nice, it only makes a distinction between letters that have 0 holes, 1 hole, and 2 holes. And the simplest convention that you can sort of come up with for representing that is like having a 0 hole letter be just like a vertical line, a 1 hole letter being like this like O shape, and then a 2 hole letter being this like sort of figure 8 shape. Hopefully those are clear there. And yeah, this is really the most simple fundamental one because the 2 specifically needs to have 1 blank space for either one. So your letters need to at least be 5 by 3 wide. Now you can write C1 using the above convention, and to sort of hide C2 inside of there, you can actually write it on the bottom of a letter that has either 1 or 2 holes. And something that you can notice about the letters that you're given for the colors is that all of the colors you're given will always have at least 1 letter that has 1 or 2 holes. So you can always be able to sort of hide C2 in the bottom of one of them. And that's it. So we're halfway through. Let us progress. Okay, yeah, ground control. This is a fun one. So you want to come up with some path between two hills, hill 1 and hill 2, such that the difference between the maximum and minimum height is minimized. You want the hill to be as globally flat as possible, if that makes sense. Now, the approach that you can use for this is to set some h minimum. So take all the heights, start with the lowest height of the lowest hill, and say, okay, this is the lowest height I will have for all of the hills I'm going to take on my walk. Let's see if this is possible. Then for your h-min, you can add, sorry, so for your h-min, you can add edges if the h is greater than or equal to h-min and is in order of h-max. So I said the wrong thing there. When you set h-min, that's actually the smallest minimum that you want. So you're saying, I don't want any hills to be shorter than this h-min that I set. And then you can sort of add hills to this walk, starting with whatever your h-min value is and going in increasing order until hills 1 and 2 are connected. If they are connected, you can be very happy. You can record the h-max that was required to connect the hills between h-min and h-max, and then that is your height differential. If you are unable to connect your hills together, then you need to set a different h-min. And so you can actually just do it for all of the h-min. This will give you a solution that is O of n squared log n. Because if you do sort of like Kruskal's algorithm, sorting the edges and adding them in increasing order until the components with hill 1 and hill 2 are connected, that's going to take n log n time, and you may have to do that for n hills because each hill may have a unique height to start with. So you could pick a unique h-min for each one. But you have enough time to do that because the input is quite small. I believe it's n is like 5 times 10 to the 3. Moving on, we have enclosure. So we need to find the polygon with a maximal area such that the perimeter is equal to d minus 2. Is that 2 nm? I'm not sure, but anyway, you lose some amount of time for every marker you place down, and you have some amount of starting time. So there are a couple of observations that you can make in this problem. The first one is that the polygon has to be convex. The reason the polygon has to be convex is if you have some pair of edges that cause some kind of concavity, you can always sort of flip those edges outwards to be facing out like that, and you wouldn't lose any perimeter. The perimeter would be the exact same, but the area would be larger. So it should always be convex. The other observation you can make is that the polygon needs to be a regular polygon. If you have some pair of sides that add up to some constant, and you have like a short side and you have a long side here, you can always sort of pull the intersection towards the middle so that the short side and the long side are equal to maximize the area. And the area of this triangle is going to be bigger than the area of this triangle. That's like a local minimum property of triangles. The third observation that you should probably make is that if you use just like a bunch of markers, too many markers, you're going to spend a bunch of time putting down markers, so your answer is going to be very small. And as you add more markers, your answer will approach 0. However, if you use too few markers, you won't be capturing much area in your polygon because a square captures more area with the same perimeter compared to a triangle, and a pentagon captures more area compared to a square, and so on and so forth. So the more edges you have, the better, if the perimeter is the same. But obviously, the more vertices you add, the less time you have to actually draw out that perimeter. Since there is some kind of local maxima, you can use ternary search to figure out what the answer is. The answer being the optimal number of points, and then you can just use geometry to figure out what that area is. What's enclosure? I really like that one. Moving on to the last few, there is Brickfields here. Brickfields is an actual name of an actual cafe in my actual suburb, Redfern. It's a great cafe. I'd recommend going. And so in this problem, Brickfields, given a bunch of rectangles, you need to check if it forms a complete wall. So whether the bounding box formed by the rectangles, every point within there is covered by exactly one rectangle. Now, to prove this, there are two things you need to check. First of all, do the areas of the rectangles that I'm given add up to the area of the bounding box? This is pretty simple. The areas width times height. Just add up the areas of the rectangles, and if they're equal to the area of the bounding box, then you know that the area is all good. The completeness check, is every part covered by exactly one rectangle? That is a bit harder. But what you can do is you can do a line sweep for every rectangle, going from either top to bottom or left to right or whatever order you care about. And whenever you encounter a rectangle, you're going to add an interval corresponding to sort of the opposite of the direction that you're going in. So if you're going from left to right and you encounter a rectangle, you can add an interval corresponding to its top and bottom bounds. And then when you see that that rectangle has ended, you can remove that interval from your set. If your set either has two intervals that are overlapping, that means that there has to be two rectangles that are overlapping. And so you know that your answer, your given wall cannot be correct. Now, to do this line sweep, you're going to have to sort the rectangles by some convention, whether that's by the sort of height that they start at, or whether it's the width that they start at. Not width and height, sorry, like the x and y that they start at, I guess I should say. So that's going to take an long time. But then, the rest of the stuff is going to be, I guess technically going through this would also be n-log n if you're like adding and removing to a sorted set. But that's going to be the time for your Brickfield's problem. The final problem, and I think probably the hardest, although not too hard, is another round. So you have a bunch of pubs, and they all close at different times, and you want to drink as much beer as possible because you're an alcoholic. And so you're going to travel between the pubs drinking pints. You can't drink at the same pub twice in a row. So let the DP of your address and your time equal the maximum amount of beers, maximum amount of pints that you've been able to drink at this time, ending at this current address. Now, the first thing you want to do is pre-calculate the distance between all the pubs, because you're going to be moving through pubs a lot, and these distances are not going to change. So it definitely helps to pre-calculate them. Then you can use Floyd Washer for that. DP for some address at some time is equal to the DP at some other address at some time plus the amount of time it takes to travel between the two places, plus the amount of time it takes to travel the ith pint. And this changes depending on which pint you're on. So you got to be using these sort of current values of your DP as indexes for how long your current pint will take.
Sorry, were you guys discussing?
We can only go from or between two pubs if we have enough time to A, travel there, and B, actually drink the pint once we get there. Because half-drunken pints don't count. If you get kicked out while drinking a pint, does not count. But this is a fairly simple dynamic programming relation. Once you get it, you just be able to iterate through all of them. It's going to take if you do Floyd Warshall, I guess it would be n cubed. But the input is still quite small, so that is all good. Oh, my camera angle is off. Oh no. I hope you guys can see my algorithm.
You yourself were not in frame, Tom.
Oh, that's fine. They don't need to see me. That's all good. Anyway, that is all. If anyone has any questions about the problems, feel free to ask. I would like to thank the amazing, incredible, fantastic UK IEPC, that's the UK and Ireland competitive programming contest, for providing these problems. I'm a big fan of them. That was from the 2025 contest. And ps2aucpl.com, that's the Adelaide's contest if you want more fun programming problems. Yeah, thank you so much, everyone, for attending, and I hope you have a good one. Yeah, bye-bye.
Could I trouble so you said we had pizza, therefore we missed your entire editorial.
Oh, you missed my whole editorial? Oh, wait, I can do it again. I still have my voice. I was wondering why I only just saw you guys sit down. It seems strange.
I'm gonna leave the mic on so you can talk about this.
Yeah. If you guys have like any questions about any particular problems, just let me know, and I'm happy to answer them live.
Yeah.
I'm just at work, so I'm not doing anything important.
Thank you. Any requests? Which problem do you want to see discussed? Problem C, Jack.
Oh, C.
Yeah, Tom, we had feedback about problem C.
Oh, you guys weren't a fan of the amazing input-output that is problem C?
What thing?
Is it just
So problem C.
I was like reading it.
Yeah, so there is a lot of ways that you can
Do like a 1-5-1 task.
Yeah, problem C was really tough.
Oh, I can get the answer with don't go.
Yeah. So you can write your C1 as a series of like these three characters. So if it has 0 holes, you can represent it as like just like a line. If it has 1 hole, you can represent it as like this like O shape. And if it has 2 holes, you can represent it as this like O shape with a line through it. It kind of looks like a B. These are kind of like your fundamental symbols. You can't get anything simpler with 2 holes that is less than 5 by 3. So you can write C using any of the above because to write C1, we only make the distinction between characters with 1, 2, and 3 holes. To hide C2 inside of there, you can make a character either with 1 hole or 2 hole sort of wider to fit your purposes, and then sort of fit C2 along the bottom. And the interesting thing with the input that you're given is that every word that you have will at least have 1 letter that either has 1 or 2 holes. So you'll always be able to put C2 along the bottom of a letter that either has 1 or 2 holes in it. There's a lot of ways to solve it, but that is how I would do it.
Can we do E?
E, enclosure. This is my favorite one. I love it. You have to find the polygon with the maximum area such that the perimeter is equal to D minus like 2 and M. So there is a couple of observations you need to make about this question. The first one is that the resulting polygon needs to be convex. That is because if you have some like pair of lines that go inwards, you can always flip those lines to go outwards, and the perimeter will be fixed, but the area will increase. The other observation you can make is that the polygon has to be regular. If you have some pair of edges, one short and one big, that add up to some constant number, you can kind of pull this pivot towards the middle, such that the 2 edges are of equal length, but they still add up to the same number, and this will actually increase the area of the triangle. Optimal triangles are always like, symmetrical. Now, something else you can notice is that if you spend all your time putting down markers, you're not going to have any time to move. So as the number of markers approaches infinity, your area will approach 0. The other thing you need to realize is that shapes with more edges do a better job at enclosing space. So if you have like a triangle with a fixed perimeter versus a square with a fixed perimeter, and those perimeters are the same, the square is going to include more space. And so on and so forth. As you may know, the circle is the best shape that it captures the most space per area. And as you add more edges, you'll sort of approach a circle. So on one end of the extreme, it's like not very good. And at the other end of the extreme, it's like not very good. And there's some sort of local maximum in the middle, so you can use ternary search to find the correct number of edges. And then, once you've done ternary search, you can just use some basic geometry to figure out the area of your polygon.
Yeah.
I hope that helps.
Oh, yeah, we have to agree. It's like a maximum on the middle.
G next?
What's up?
G next? G?
G, ground control. Okay. So in the problem ground control, your objective is to minimize or have a path where the maximum hill on the path minus the minimum hill on the path, this metric is minimized. So you want sort of the globally flattest path. I think an approach for this problem is to set some h-min. So you set some h-min, you say, this is going to be the minimum hill on my path. I'm not going to have any hill that is shorter than this. And then you can sort of sort the edges and add them only if the current edge includes a hill that is the current edge includes both hills that are greater than or equal to h-min. And you can add these edges in order of their h-max. So you can sort of add the edge that's closest in height to your selected minimum height and the next closest, so on and so forth. It's very similar to your Kruskal's algorithm. Once hills 1 and 2 are connected, you can figure out what h-max you had to use, or sort of, if I could rephrase it, what is the largest h-max you needed to connect these 2 hills. H-min is fixed, so you can take the difference between them. And then you can do this for each of your h-mins. I wrote here that it's n log squared log n, but I think If you use binary search over h-min, you could actually probably get better than that. I think you could get n log n. But I haven't tested it myself. Yeah, I hope that's clear. I like that question.
We do T.
D. D. Oh yeah, this one. I like this one. Hopefully you guys can read that. So for D, we have some sort of relations where we have to sort of create a sorted string that follows those relations. So if A is less than B, then all of the A's occur before all the B's. And something to note is that it's transitive. So if A is less than B and B is less than C, therefore A is less than C. What we can do is we can make some kind of Floyd-Warshall matrix where if A is less than B, then that is true. So Floyd-Warshall A is B is true if A is less than B. You can also do greater than. It depends on what convention you want, as long as you're consistent. Then you can do n iterations where n is the number of edges, which is 26 because the alphabet is small, to figure out if there are any cycles. So if any point along the path, like once you're done with your Floyd-Warshall, if A to B is true and also B to A is true, then you know that you have some kind of cycle. So you know it's impossible. So you can do your Floyd-Warshall for 26 iterations, iterate through all of them. If there's a contradiction, then you're impossible. How do you get the actual string that you want? There's a couple of ways you can do it. You can take the original letters you're given and then also do a topological sorting through the graph to figure out the ordering. Another thing you can do is actually write a custom comparator that uses the result of your Floyd-Warshall, which is pretty cool. But yeah, just one of those standard ones to create some kind of ordering on the nodes you can use to help sort of sort out your string.
I have a question. How does this deal with if like A and B have a cycle? Can you just not use either one of them?
No, you have to use all the letters that you were given in the input string. So Jamie has an idea. He's like, I want this input string. You can sort it any way. So if that input string has an A and a B, then you need to use both of them. But if there is a contradiction, you can output impossible. And if you finish your Floyd-Warshall pathfinding and there is a path from A to B and a path back from B to A, then you know there's a contradiction.
Right. So what if you have the case where you have A is greater than B, B is greater than A, and then let's say the word Among Us, right, which has one A. Okay. In that case, you don't have to use B, right?
Oh yeah. I suppose a caveat for this would be you can structure Floyd-Warshall grid with only the letters that are used in the input. Is one way you could do it. Or you could do some extra exemption logic, this blah blah blah, this letter doesn't count. But that's probably how I do it. Yeah. Yeah. Good question though.
Can we go over A?
Oh yeah, sure. So it's this one here. I hope the light is not in the way. These lights suck. I'm at work right now. Okay. So A is a fairly, I would say, standard 2D DP. So let dp of your current position and your current time be equal to the maximum number of beers that you could drink to get to this current position and this current time. Specifically after you have drunk a beer is what this convention is. The first thing you want to do is pre-calculate the distances between all the bars. You may want to go bar hopping quite a lot because you can't go to the same bar twice. So pre-calculating this will help keep your complexity down. Now we have some kind of relation. If you want to go from bar X to bar Y, then you have to pay the cost of the time that you have taken to get to X and drink that many drinks, plus the time it is going to take for you to go from X to Y, plus the time it will take for you to drink your next pint at Y. And if all of these is less than your limit, then you can make this DP transition. And so yeah, we can only go from X to Y if we have enough time. So if we can do dxy plus dy. And that's basically all there is to it. The dimensionality is addresses. This is the number of there's the number of hubs. and then the time, that's like your time limit. But if you multiply those together, you get a complexity that is not too bad. A complexity that's good enough. I don't remember what the constraints are. Yeah, I would say that was probably the hardest one in the set.
Can we please try problem H?
Problem H. Oh yeah. This is this one, I believe. This is yeah, hit the road, reference to hit the road Jack, because Jack is the character, also one of my friends. For hit the road, you have a list of integers, and you want to minimize the largest gap between adjacent integers. So first of all, you can iterate through the list and figure out what that existing largest gap is. Then you can iterate through the list again, comparing elements that are 2 apart. So you want to compare indexes 0 and 2, then 1 and 3, then et cetera, et cetera. And then you can figure out what that gap would be if you remove the element in between. And then just take the minimum of the result. So you may have a result where you can remove an element and it won't increase the largest gap because the largest gap would already be bigger. If that's not the case, then you can just take the min. Yeah, thanks for asking. I think we've almost gone through all of them now. I think we haven't done B and F. If you guys want either of those.
Oh yeah, actually B is really.
Yeah, let's do B.
Yeah.
Want to do B?
Thank you.
Thank
Yeah,
you
let's
so
do
much.
B. B, Brickfields. Brickfields is a name of a very real cafe in my very real suburb of Redfern, which has very good almond croissants. I'd recommend going there. Anyway, you want to check if a wall is complete, so you're given a number of rectangles. You want to know if this completely covers the bounding box that encloses those rectangles, while also not covering the same point more than once or less than once. Now, there's 2 conditions that you need to know if a wall is complete. First of all, do the areas of all the rectangles that you're given add up to the area of the bounding box? This is pretty simple. You just take all of the rectangles, do base times height, and then see if that adds up to the area of the bounding box. If it doesn't, then you know you don't have enough material to win, or you have too much material to win. The harder part, I would say, would be figuring out if any 2 rectangles overlap. Because if they do, then you obviously know that you don't have a valid wall. And I guess an important thing to note is that if 2 rectangles overlap, you know that there has to be a place where there is absolutely no rectangle over that point. If the area matches the area of the bounding box, if you take away some, you can add some to another place. Anyway, to do this completeness check, you can do a line sweep for all the rectangles. You can either go from left to right or top to bottom. Sort the rectangles by their starting points with either of those conventions. And then you can sort of add the interval that is represented by that rectangle when you first encounter it in your line sweep. So, if you're going from left to right, you can add the top and the bottom coordinates of that rectangle as like an interval to your set when you encounter it. And then when that rectangle is finished, you can remove it. Now, if you're going through this line sweep and there's ever 2 intervals that overlap, that means that there are 2 rectangles that overlap at the same point. So you know that it's impossible. If you can get through the entire line sweep and this never occurs, then you know that all the points are covered correctly.
Your opinion on like 2-dimensional symmetry or like symmetry? You can just do it with like some optimizations, right?
I don't know.
What's that?
Oh, what's your opinion on like 2-dimensional symmetry?
My opinion of 2D segmentry? Oh, for this problem?
Yep. I'm pretty sure it passes because like you can just like set the like compressions, right? And it should be fine with the like where you don't need to like expand into like smallest node where there's like 1 element, and I think that optimization just should do it.
Yeah, like I feel like I could see that working. You could query each of the points, or like query each of the ranges of points, and then figure out how many rectangles are there if you insert them all into the tree. Yeah.
I believe the only difference is like if you do it this way, like, and you can check if it's a rectangle, even though like you can allow the overlap.
Sorry, what was that?
So even if you allow the overlap, you can check if it's just a rectangle with no holes in it, like this way.
Oh, right. Oh, yeah. Is that how you solved it?
I mean, I didn't implement it, but like.
I feel like that could have worked. I feel like you should definitely try implementing that.
I
the
did solve a
problem-
different problem, and it was like quite similar. And I believe it's like IOI in 2014, and it's the second problem, I believe.
Oh, and it's like a similar problem.
Yeah, it's very similar. It's,
Uh,
but like you need like heavy like optimizations with your like symmetry, and it's just two-dimensional symmetry, and like should be fine after that.
oh, interesting. Yeah, I think this one definitely does not require as much, but if you can do it with a sec tree, that's great. I often accidentally use sec trees for problems I don't need them, like in like coded contests and stuff. And that always gets me sometimes, but it's always cool to be able to apply these kinds of data structures to things. So yeah, no, thanks for the comment. I think I'm gonna try and do that as well. See if it's possible.
So Tom, is this sufficient to conclude that there are not gaps between the rectangles either? Because you're only checking for overlaps. So my guess is
Yes.
the area bounds plus no overlaps, like sort of implies that they're tightly packed.
Yep.
Exactly, because if you have an overlap, that means that somewhere else there has to be a gap if the area is the same. Because if you add to one area, you have to take away from somewhere else. Yeah. Cool. All right. Good job, guys.
Thanks, Tom.
That's all good. That's all good. I hope you enjoyed the contest. Looking forward to seeing you next time. I believe it's May 19th, if you can make it. It's a bit far away, but yeah, no, very cool to see you guys again as well. I miss y'all. Wish I could be here, but I hope in the meantime you have a good time.
5 weeks.
Thank you.
Okay, see ya.
Thank you.
Right.